Assalamu alaikum students. Today we start next topic about exercise 3.2. First we discuss about field like group in last chapter with 5 properties: clear property, associative property, identity, inverse and commutative property. Which set hold these properties is called group. Now field. The set F is called a field if the operation of addition and multiplication on F satisfy the following properties. First is clear with respect to addition and multiplication, commutative property, associative with both operations addition and multiplication, identity 0 and 1 both are hold in this set, and then inverse. And then a new property for this is distributive property, in which set if all these properties hold is called field. Now some properties of addition: matrix addition, scalar multiplication and matrix multiplications. If A, B and C are n cross n matrices and C, small c and d are scalars, the following properties are that commutative property with respect to addition: if we add two matrices A plus B or B plus A gives same answer. WRT means with respect to. Associative property with respect to addition also satisfy. Associative property of scalar multiplication. Scalar multiplication means we multiply a matrix with a number. Existence of additive identity. Additive identity is 0, null set. A plus 0 or 0 plus A gives same answer is equal to A. Existence of multiplicative identity. Multiplicative identity is I 1 0 0 1. If we multiply with A from left side or from right side, it gives the same answer. Distributive property with respect to scalar multiplication also satisfy. Associative property with respect to multiplication. In this order we multiply 3 matrices, it gives same answer. Left distributive property: if we multiply B plus C from the left side with A is equal to product of AB and sum of with sum product of AC. Right distributive property: we multiply A plus B from the right side with C. Both properties satisfy in matrices. And then property 10, a scalar number C multiplied by the product of AB gives the same answer. Or associative property. Next here is example. We have two matrices A and B. And we find AB and BA in matrices order are very important. If we multiply A, B, we will first write A and then B, and multiplication with the same process we have done in last exercise. If two matrices are multiplied, first column and second rows are same. In this form, they both have same order. Now we multiply first row with the first column of B and first row of A, multiply by second column of B. Then we multiply first row with the third column of B. In same process, we multiply second row with the first column, with second column, and with third column. Horizontal line is row and vertical line is column. And then we find BA. We first write B and then A. In same process, we multiply these matrices, but the answer is changed. Therefore, commutative property of multiplication is not hold in matrices. Next, another example. If A is a matrices of order 3 cross 4, 3 rows and 4 columns, we have to find A multiplied by A transpose and then A transpose whole transpose. First of all, we taking its transpose. In transpose, we change rows into column. First row become first column. First row is 2 minus 1 3 0. Now it becomes first column 2 minus 1 3 and 0. And second row 1 0 4 2, it becomes second column, and third row become third column. Now we multiply these two matrices. First we write A and then A transpose. In A, order is 3 cross 4, and in A transpose, order is 4 cross 3. First column and second rows are same, therefore they can be multiplied. Now we multiply these with the same process. First row with the first column, then second column, and then third column. And then we multiply second row with the first column, with second column, and with third column. And same third row, multiply all 3 columns. And in second we find A transpose, and then again its transpose. So it shows the same answer is equal to A. If we transpose again and again, it becomes the same answer with in the original form. Now determinants. In 2 cross 2 we read about this. A are matrices of order 4 cross 4, and then is determinant. In matrix form we write bracket around it, and here we draw the straight lines, and straight line form is called determinant, and this form is called matrices. Minor and cofactor of an element of a matrix or its determinant. Consider a square matrix of order 3, then the minor of an element A ij denoted by capital M ij, and the determinant of the 3 minus 1 and 3 minus 1. By deleting the ith row and jth column. For example, we have a matrix in general form, then the matrix obtained by deleting the first row and the second column, it becomes like that. If we delete first row and second column, the remaining values are there, and this is called cofactor of A12, and its determinant is called minor 1 2. We delete rows first row and second column, so it is called minor 1 2. M12 means we delete first row and second column. 1 shows row, 2 shows column, and the remaining values in this determinant. Then is cofactor. The cofactor of an element noted by A ij is defined by -1 raised to power I plus j multiplied by minor. If we multiply minor with the position sign, it becomes cofactor. In last example, we have the minor 1 2, and we will multiply it by -1 raised to power 1 plus 2, it become cofactor. Minor 1 2 is equal to the values which lead from the above matrix first row and second column, the remaining values in the determinant, and then we multiply it by -1 raised to power 1 plus 2, it become cofactor. Determinant of a square matrix of order n greater than equal to 3. We expand it from first row like A11, and then we multiply it by its cofactor A11, then A12, and multiply it by its cofactor A12. Then in the same way we can find their determinant. If A is a matrix of order 3, we write it as A12, A11, A12, A13 first row. A11 means first row, first column. 12 means first row, second column. 13 means first row, third column. And in same way, A21 means second row, first column, second row, second column, and then A23 means second row, third column, and its determinant is in the third row A11, then it multiply by A capital A11 plus A12 multiply by cofactor A12. Small a means element and capital A means cofactor, and A13 multiply by cofactor A13. And in next we can find determined by any row and any column. Mostly we find it from the first row, and then we replace cofactor with their values. A11 means minor A11 with its sign. If a sum of its index is even, it shows positive, and if the sum of its index is odd, it's negative. Similarly, one can be written as determinant of A is equal to A11 minus A11 minus A12, and same in the last plus A13 minus A13, and we replace minor with their values. Minor M11 means we drop first row and first column. If we drop first row and first column from this matrix, first row and first column, we name the value A22, A23, and then A32 and A33. And same process we write M12 and then M13, and then further we solve their determinant. Cross multiply, we multiply their diagonal elements, and in between them a negative sign, and this is the determinant of 3 cross 3 matrix. Here we have an example for determinant. Now we write determinant formula A11 minus A11 minus 12 minus A12 plus A13 and minus 13. For we replace A11 by its value. A11 means first row, first column. Its value is 1. Minor A11, we delete first row and first column. The remaining values is 3, 1 and minus 3, 2. A12 minus 2, and its values we drop first row and second column, minus 2, 4 and 1, 2. And then A13, its value is 3, and minor 1, 3, we drop the value first row and third column, and then values minus 2, 3 and 4, minus 3. and then we find their determinant. In first determinant, we multiply 3 into 2 and then minus sign, 1 multiplied by minus 3. In second determinant, we multiply minus 2 by 2 and then 1 by 4, minus 2 by minus 3 and then minus sign, 3 by 4, and simplify and get the answer. Now in this example we find cofactor A12. First we find their minors. M12 means we delete first row and second column, the remaining value in the determinant minus 2, 4, 1 and 2, and we find the determinant minus 2 multiplied by 2 minus 4 and 1 multiplied by 4 is also 4, and between them the minus sign of formula, it is equal to minus 8, and then further we find M22 and then again, and cofactor A12 is equal to minus 1 raised to power 1 plus 2 and then value of minor 1, 2. Okay, next we find its determinant. Determinant is equal to A11. It depends on from which row we expand it, and the same way we find the determinant. Try to solve its determinant from first row. Next, properties of determinant. For a square matrix A, determinant of A and its determinant of its transpose always same. You will find determinant of A and then find determinant of its transpose, they always same. If in a square matrix A, 2 rows or 2 columns are interchanged, the determinant of the resulting matrix is change with the negative sign. In transpose case, value is same, but if we change 2 rows or 2 columns, their determinant sign change with the negative sign. If a square matrix A has identical 2 rows or 2 identical columns, then determinant is 0. If in a determinant 2 rows or 2 columns are same, then its determinant is 0. If all the entries of a row of a square matrix A are 0, then determinant is 0. If all values of a row or column are 0, then any row or any column, then its determinant is 0. If the entries of a row or column in a square matrix are multiplied by a number k, then the determinant of the resulting matrix is Ka. We find a determinant of a matrix then we multiply its row by 2, then again we find its determinant, we give the answer with, if we multiply the previous determinant by the same scalar value 2. If each entry of a row of a square matrix consists of 2 terms, then its determinant can be written as the sum of 2 determinants. If each entry of a row or a column of a square matrix consists of 2 terms, then its determinant can be written as the sum of 2 determinants. If we break a column or row into 2 numbers, then we can write it in the form of like that. If we draw a11 plus b11, we write a11 in first determinant and b11 in second determinant, and original determinant is equal to the sum of these two determinants. The sign are missing. First we write the determinant b equal, then these two determinants with the sign of plus. If to each entry of a row of a square matrix added a non-zero multiple of the corresponding entry of another row, then the determinant of the resulting matrix is same. If we multiply any row by any column, any number, then it add in the another row, the result is same, no change in the determinant. If a matrix is in triangular form, then the value of its determinant is product of the entries on its main diagonal. Triangle form means in a matrix below diagonal or above diagonal the values are 0. This determinant is called triangle, and its determinant is obtaining by multiply the values of the diagonal. Now I prove the above mentioned properties of determinant. In first property, rows and column of determinant are interchanged, then the values of determinant does not change. Example, we find the determinant of the first values, then we change their rows and column, and then again we find the determinant, the answer is same. In second, the value of determinant change sign if any two rows or column interchange. We first find the determinant, then we change rows and column position, and then we obtain the negative sign. If all the entries in any row or column are 0 like that, then its determinant is 0. We expand here with the column 1, the determinant is 0. If we expand it from any row or any column, the answer is 0, because all entries in first column is 0. If any two rows of determinant are identical, the values of the determinant, now here first two rows have same values, then its determinant is 0. If any row of determinant is multiplied by a non-zero number, the value of the new determinant become equal to k times the value of original determinant. Here we have a determinant. We multiply first row by k, then again we find its determinant. It is equal to k times the original determinant. Property 6. In first column we have sum of two values and we write it in two determinants, and from first column we write a in first determinant and b in the second determinant. Property 7. If we multiply any column by k and add into the any column, the determinant of both of these values are same. Now here we find determinant of 4 plus 4. First way is the original way, like we find determinant of 3 cross 3, we expand it by the first row, but here we reduce it in the form of 3 cross 3, like we first arrange first column with the help of row operation. We make all three values equal to 0, like in last row the first entry is 1, we multiply it by -2 and add it in the first row, because in first row first element is 2. We multiply fourth row by -2, all of its 4 element, and add in the first row, we become new values 0 0 3 0. Now see in second row, its first element is 3. Now we multiply fourth row by -3 and add in the second row, and we become the value 0 4 3 -7. And in third row we have the first element -5. We multiply fourth row by 5 and add in the third row. Now the new determinant is 0 0 0 and 1, and we expand it by the first column. First value is 0, its cofactor. Second value is 0, its cofactor. Third value is 0, its cofactor, and fourth one is 1 and its cofactor. So first three values going to be 0, and the last one is with its determinant. Fourth row first column, we eliminate fourth row and first column, and we obtain the values, and then we find its determinant with the process of 3 cross 3, and we get the answer. This is the short way to make any row or any column 3 of its values equal to 0, and then we find its determinant, change it in 3 cross 3. Calculation are difficult, but make it is short. It depends on your calculation. Now we have determinant, but we show it equal to 0 without expansion. Now in this determinant we multiply -1 with column 1 and then add in the second column. If we multiply the first column with -1, it becomes minus x minus x minus x. Add in the second column, we cancel x by x, and then we call common x from first column. In determinant, we common from any row and any column, but in matrix we common from the whole matrix. This is the difference between matrix and determinant. If we common from matrix, it common from the whole matrix, but if we common from the determinant, it common only from any row or any column, depend on our calculation. Where do we find it? And next step is we subtract column 2 minus column 3. It also becomes 1. Now the property 5 apply on there. First two columns are equal, therefore the determinant is 0. Repeat these steps again and again, and then we learn how to find it. Now we solve the equation to find the value of x. Here we again some calculation, make it easy by adding the columns. We'd add column 3, column 2, and then column 4 and column 2. Expand by row 2 because their maximum value is in 0. In row 2, first value is 0, then 1, then 0, and then 0. 1 in place. If we solve it with 1, its position is second row and second column. We delete second row and second column and remaining values in the determinant. And here we multiply row 2 by 2 and add in the third row. This makes the last value equal to 0. Now 3 common, x minus 3 common from R3. And x is equal to minus 3, and in the determinant it is equal to 0 if the first row and second row are same. How it becomes same? If we replace x by 0, therefore value of x is equal to 0. Complicated, but if we solve it, then it make it easy. adjoint and inverse of a square matrix of order n greater than 3. We first find the adjoint of 2 cross 2. We change the position of first diagonal and sign of the second diagonal. Now but here is adjoint of a matrix of order equal to 3 or greater than 3. Here we find its inverse. We first find the cofactor of the element of A. Now how many cofactors are there? 9. A11, A12, A13, then A21, 22, 23, 31, 32, 33. All cofactors just like A11. How we find this? We eliminate first row, first column, and minus 1 raised to power 1 plus 1 and find a determinant. And next A21 we eliminate second row, first column, and minus 1 raised to power 2 plus 1 and find its determinant. Now all cofactors, how many cofactors? 9. Find all these cofactors. And then we replace in its matrix form, and its adjoint is its transpose. We write cofactor in matrix form and then taking its adjoint or transpose is called its adjoint. And then determinant of the original matrix, and we divide adjoint by its determinant, and it becomes the inverse of 3 cross 3 matrix. Now here we find product of AB and its transpose. It becomes B transpose and A transpose. We first multiply AB, first row by first column, then first row by second column, and then third row by first column, third row by second column, third row by first column and by second column. Then it's transpose. Then we find transpose of B and transpose of A and then multiply, and we get the same answer. Now this is the last topic for 3.2 and 3.3. Do these examples and definition, and then we solve in the next lecture these exercises. If you have any problem, reply me. Jazakallah.